Here are some problems related to our topic, functions and performance of evaporator, condenser, and expansion devices. Guided problem solving number 1. Heat is absorbed from a cool space at 22 degrees Fahrenheit at a rate of 320 BTU per minute by refrigerant 22 that enters the evaporator at negative 12 degrees Fahrenheit with a quality of 0.3 and leaves a saturated vapor at the same pressure. Determine the volume flow rates of refrigerant 22 at the evaporator inlet and outlet, the rate of exergy destruction, and the evaporator in the evaporator and the exergy efficiency of the evaporator. We take our ambient temperature to be 77 degrees Fahrenheit. First is we need to draw the diagram. So this is the diagram showing the different points and the interactions, heat interactions in the evaporator. And we are given with the temperature at the inlet of our evaporator as negative 12 degrees Fahrenheit and a quality of 0.3. And at the outlet, we are given with a saturated vapor. That's why our quality is 1.0 and the temperature is the same because it is at the same pressure and at that particular saturation points. So we tabulate the properties. Since we are given with a saturated vapor at 0.2, then we can solve for the different properties at this point. We have saturated vapor at negative 12 degrees Fahrenheit and a quality of 1.0. Then we can use our software to get the enthalpy. So since we are given with English units, you can use the English units of the software to get the BTU per pound mass, and that is 170, and the specific volume, and that is 1.75 cubic feet per pound mass. So we already have this value from the software. And since we only know the quality at 0.1 as well as the temperature, and since this is a mixture, we have to use equations for mixture to get the enthalpy and other values. So to calculate the enthalpy at the inlet, which is at 0.1, so we will use this formula since this is a mixture. So we can use the mixture formula. So H1 is equals to HF plus X1 Hg minus HF. So using the software, at negative 12 degrees Fahrenheit for refrigerant 22, we can get HF and Hg as follows. And since we already have X1, we just substitute these values so that we can get the value of H1. And H1 is 102.82. So that's why our enthalpy is 102.82 at the inlet. For the specific volume, we will use the inlet points, we will use the same formula, but this time in terms of specific volume. So we can get VF and VG at the software using our temperature, which is negative 12 degrees Fahrenheit. So substituting, we can get now our specific volume at 0.1 to be 0.53 pound mass per feet cube. So we have it here. And finally, since our entropy is also needed here because we are to look for the rate of exergy destruction, we have to get also the entropy. So for the saturated vapor, we can use immediately the software. And for the entropy for 0.1, we will use the formula. Using the same method, we can get the entropy at 0.1 to be 0.28 pound mass per feet cube. 0.28 pound mass per feet cube. Now we already have the quantities that we will need to calculate the unknown. So for the first unknown, the volume flow rate at the evaporator inlet and outlet. So the relationship between the volume flow rate is in terms of the mass flow rate. So we need to get first the value of the mass flow rate of the refrigerant. So using the formula, refrigeration capacity over refrigeration effect, which is QL over H2 minus H1. So from the given, we are given with the refrigeration capacity, which is 320 BTU per minute. So this is the heat that we are extracting from our cold space. So substituting as well as the values from the given, then we can get the mass flow rate as 4.76 pound mass per minute. We use this one to get the inlet volume as well as the outlet volume. For the inlet volume, we can use the formula V1 is equals to M V1, which is the specific volume at point 1. So from the table, so our V1 or the inlet volume flow rate is 2.52 feet cube per minute. For the outlet volume flow rate, that is mass times the outlet specific volume. So we have 8.33 cubic feet per minute. Next is we calculate the rate of exergy destruction and exergy efficiency. So we will use our formula for the rate of exergy destruction for evaporator, and this is given by this formula. So take note that our Q here is the refrigeration effect. That is H2 minus H1. Our TL is our temperature of the refrigerated space. However, our TO is given, and that is 77 degrees Fahrenheit, and we need to convert that to Rankine so that we can use this equation. So substituting the values for the mass flow rate, we have TO, the entropy at 0.2, entropy at 0.1, our H2 minus H1, and the temperature of the refrigerated space in Rankine. Then we can get the exergy destruction as 31.14 BTU per minute or 0.57 BTU per second. And finally, for the exergy efficiency, we need to use these equations, and since we already have all of this, we just have to substitute them. So by substituting our refrigeration capacity, our TO over TL, as well as the other quantities, our exergy efficiency of the evaporator is 46%. So take note that requirement is for us to have a higher exergy efficiency, because higher exergy efficiency means a high quality system. So this is opposite of our exergy destruction. Guided problem solving number 2. The refrigerant 134A enters the condenser of a refrigeration cycle at 800 kPa and 60 degrees Celsius with a flow rate of 0.095 kg per second and leaves at the same pressure, subcooled by 3.3 degrees Celsius. The refrigerant is condensed by rejecting its heat to water, which experiences a temperature rise of 11 degrees Celsius. Determine the rate of heat rejected in the condenser, the mass flow rate of water, the coefficient of performance of this refrigeration cycle if the cooling load at this condition is 12 kW, the rate of exergy destruction in the condenser. We take TO as 25 degrees Celsius. So this is our condenser. As you can see, we are expending heat or expelling heat to the environment between 2 points 1 and 2. We are given with the properties at point 1, and that is 800 kPa and 60 degrees Celsius. And at point 2, since this is the same pressure, so we have 800 kPa at point 2. So this is an isobaric process. So we tabulate the properties that we can get using the given. So it enters as superheated vapor at point 1 and goes out as a subcooled liquid. Based on the given, it's subcooled by 3.3 degrees Celsius. That's why it's not saturated, but it's a subcooled liquid at point 2 at the same pressure. And since we are given with two properties at point 1, we can immediately get different properties using our software. So take note that here we included the saturation temperature at this pressure so that we can get the subcooled temperature as well. So take note that since the liquid is, our refrigerant is in a vapor state, you can see that our temperature is higher than the saturation. So meaning our assumption that this is a superheated vapor is correct. For point 2, since we are given with a subcooled, so the liquid has been subcooled by 3.3 degrees Celsius, meaning it is 3.3 degrees Celsius lesser than the saturation temperature. Because when we say subcooled, it is the temperature below the saturation temperature. And since the saturation temperature is 31.33 degrees Celsius, we can use this one. So we get the saturation temperature using our pressure. So you just use the saturation table. So get Psat at the given pressure. So we can get the saturation temperature. We need to deduct 3.3 from this one to get the temperature of the liquid. And that is 31.33 minus 3.3. That is 28.33. So meaning for this subcooled liquid, it has the same saturation temperature at this pressure, but it is subcooled by 3.3. That's why its temperature is 28.33. That's why we will not use this temperature since this is the saturation temperature, but we use this temperature and pressure to get the enthalpy, density, and entropy. So we already have our table completed. So for the first unknown, we have to calculate the rate of heat rejected in the condenser, and by using energy balance, we can get the heat rejected as mass flow rate minus H2 minus H1. So we can get the rate, so the power, because we're given with the flow rate as well. So we just multiply it with the mass flow rate, our value from the table of enthalpies. So we can get the heat rejected in the condenser as negative 19.5 kilowatt. So the negative sign means it's rejecting heat to the environment at this rate. So for the mass flow rate of water, since the heat rejected by the refrigerant is absorbed by the water in the condenser, then we can use energy balance as heat rejected equals to the heat absorbed by the water. And for the water, we can use our formula mCp of the water multiplied by delta T, or the temperature rise of the water. We are given with the temperature rise of the water to be 11 degrees Celsius. That's why our T2 minus T1 is 11. Our Cp for water is 4.187 kilojoules per kilogram Kelvin. So by substituting our QH, which we already have as 19.5, mass flow rate is still unknown. Then we have CPW and delta T. Then we can get the mass flow rate of the water needed in the condenser, and that is 0.42 kilogram per second. Next is to calculate the COP of this refrigeration cycle if the cooling load at this condition is 12 kilowatt. So our COP can be computed using the formula QL over QH minus QL. Take note that QH minus QL is just equals to work net. That's why we can use these heats to get the COP. So we substitute from the given, our cooling load is 12 kilowatt. So that's why our COP is 1.6. So that's a small coefficient of performance. And finally, for the rate of exergy destruction in the condenser using TO as 25 degrees Celsius, we will use this formula. So we substitute our TO in terms of Kelvin. And then for our TH, we use the same value. Since we are not given in the condenser, since we cannot use 60, we cannot use 28.33, we cannot use 31.0 because they are the temperatures at the points, but not the temperature at the average temperature in the condenser. Then we will use the same value for TH and TO. That's why we have here 298.15 and 298.15. So that's why our exergy destruction at the condenser is 0.52 kilowatt. Guided problem solving number 3. Refrigerant 134A enters the throttling valve of a heat pump system at 800 kPa. A saturated liquid and leaves at 140 kPa. Determine the temperature of refrigerant 134A at the outlet of the throttling valve and the entropy generation and the exergy destruction during this process. We take TO as 25 degrees Celsius. So this is how our throttling valve in schematic diagram. So we're given with the temperature, with the pressure at 0.1 and at 0.2. At 0.1, it is given as a saturated liquid at 800 kPa. And 0.2, since this is an MVCR, then it is a mixture at a pressure of 140 kPa. So we will use this known quantities for us to get the unknown. And since this one is a throttling valve, then it is an isentalpic process. So they have the same enthalpy. And since we have enthalpy and pressure, we can get the entropy as well as the temperature when we input these values in the software. So 140 and 240 to get temperature and entropy. So we can get our temperature of refrigerant 134A at the outlet of the throttling valve as our negative 18.67 degrees Celsius. And for the entropy generation and exergy destruction during this process, the entropy generation can be computed as just S2 minus S1. That's why we just deduct S1 from S2, then we can get the entropy generated as 0.0258 kilojoules per kilogram Kelvin. For the exergy destruction, we will use this formula. Since we are not given with mass, then our value is per kilogram. That's why instead of using MTOS gen, we just use TOS gen. So just substitute. So we can get the exergy destruction as 7.69 kilojoules per kilogram. So take note that for expansion bias, our exergy efficiency is 0.